video will cover section 3.1 exponential functions, and Ruben, could you please read that problem? Or that statement.
Just browsing, take your time. Researchers know to the dollar the average amount the typical consumer spends per minute at the shopping mall. And the longer you stay, the more you spend. So if you say you're just browsing, that's just fine with the mall merchants. Browsing is time, and as shown in figure 3.1, time is money. The data in figure 3.1 can be modeled by the function f of x equals 42.2 parentheses 1.56 close parentheses.
To the power x. Okay. So here we have the equation, and then here we have this data, and yes, it is real. I don't have the source, but it is real. And so x is representing the time, and then y, or f of x, is representing the amount of money that you spend. Now here we have a graph that it's called a bar graph, but if you were to trace, I guess, the left corner of each graph, you could see that it will form an exponential model. With my previous classes, I had them calculate how much would you spend if you're there for 4 hours, 5 hours, 6 hours, 7 hours, 8 hours. But of course, we are running short on time, so we're not going to do that. But does anyone have their calculator handy? Anyone? Okay. All right. So let's just find what will happen if you spend 5 hours at the mall. Who has been at the mall for 5 hours? Okay, me too. So let's go ahead and find f of 5. So I want you guys to substitute the exponent with a 5. 389.884. So let's round it to 88. Yeah? So let's say that if Miss Seven spends 5 hours at the mall, which it has happened, she will spend 389. That sounds about right. Yes.
Really?
Yeah. Yes. True story. Yes, it is alarming. So you'll see that once you start making your own money. Okay? So the longer you stay at the mall, the more money you will spend. And of course, that amount will increase exponentially. So let's go ahead and go to the next slide. And we're going to write down a few statements. So if you just got here, go ahead and grab the handout for 3.1. So exponential functions are functions whose equations contain a variable in the exponent like the one we've seen previously, right? So x was the exponent, that was the variable, and that is the one that gets substituted. Now, many real-life situations, including population growth, and of course decay. Remember, some countries' population is not growing, it's doing the opposite, it's decaying. Also, we have the growth of epidemics. Radioactive decay. And other changes that involve rapid increase or decrease. And they can be modeled using exponential functions. Now here on inside this box, we have the definition of an exponential function. So let's go ahead and read it. And so we have the exponential function f with base b. So this is the base. And that base could be a number. It could be almost any number, any positive number. That's what we have here. B could be any positive constant. But we have to be careful that the positive constant is not equal to 1. And we'll see in a minute why it cannot be equal to 1. We also have that x, which is the exponent. X could be any real number. Okay, so we have some examples here on the bottom of functions. And so let's see why, well, first, if they are exponentials or not. So the first four that we have on the top row, we have 2 to the power x, that is exponential, and we have that the base is equal to 2. And we have here x is the variable, that is the exponent. The next one, g of x, we have 10 to the power x, so the base is 10. And then we could see here x is the exponent, that is the variable. Next one, h of x, we have 3, that is the base, so it is a positive number. And the variable is inside the exponent, and of course we have an x plus 1. That will be something like a horizontal translation. Would you guys say it will be shifted to the right or to the left? To the left. Remember, horizontal shifting is counterintuitive, right? Now here we have something with a base that is equal to 1/2. So is that okay? Yes, right? As long as that base is positive, the base could still be less than 1, but always greater than 0. That's why we say positive. Now we have the remaining 4, and so let's see why those 4 are not exponentials. So the first one that you guys see here is not exponential because the variable is not the exponent. The variable is actually the base for that function. So what does enable that function? Quadratic. Okay, now the next one, remember how the definition says specifically that b cannot equal to 1, right? The base cannot equal to 1. And so we have one here, and if we were to make a table of values, let's say -1, 0, 1, 2. If we were to raise 1 to the power -1, what will we get? 1. We will get 1. What is 1 to the power 0? 1. What is 1 to the power 1? 1. What is 2 to the power 1? 1. Just 1. So if we were to graph that one, here's 1. So then our graph will just look like this, a whole bunch of points for all those x values. If we keep getting those more x values, we create more points, and you'll know that lines are formed out of points, right? So what type of function will that be? Constant. Oh, it's actually there. Constant function. So that's why the base cannot equal to 1. Now, if we had a base that was negative, such as that one, let's see what will happen. So if we have x and we have y, and let's say we raise, let's just take positive values. So 0, well, that's not positive, but it's not negative. So 0, 1, 2, and 3. So what is -1 to the power 0? 1. Just 1. What is -1 to the power 1? -1. Now, not Karina, what is -1 to the power 2? 1. Positive, right? Because it's negative times negative, so it's positive 1. Now, what is -1 to the power 3? -1. So you guys see how we are changing from positive to negative, positive to negative. So if I was to graph that function, that will be a 1, that's -1. 1, 2, 3. So we will have something like this. And so on. Will that be a discrete function? Continuous? Are the points connected? No. Now, if we were to choose different numbers for x, maybe they will be connected. I'm not so sure. I will actually have to graph them. Now, the last one, but definitely this is not, so that's why we say the base must be positive. Because if we have a base that is negative, once we get the y values, there will be changing, positive, negative, positive, negative, positive, negative. So that wouldn't create an exponential function. Now, the fourth one is not exponential because we have an x for the exponent, but we also have an x for the base. So that will make it not exponential. All right, so I'm going to start from 0 down, and then we'll take care of the negative values for x. So f of 0, that means that we want to substitute the x right here with a 0. So if we say 2 to the power 0, that is equal to 1. Yes? Okay. The next one, we're going to substitute x with a 1. So 2 to the power 1 is a 2. Then we have 2 to the power 2, that is a 4. 2 to the power 3, that is equal to 8. Now, if we look at the negative exponents, remember the rules for those is that if you have a negative exponent, you have to do the reciprocal of that one. Or like, in other words, remember any integer has a denominator of 1. So if we switch them or flip them, that will become 1 over 2 to the power 1. Once you do that, the exponent goes from going negative to it becomes positive. So the next one will be 2 to the power negative 2. It will be 1 over 2 squared, which is equal to 1/4. And then the last one that we have here is 2 to the power negative 3. So that will be 1 over 2 cubed, and that will be 1 over 8. So make sure you do write all those steps. Okay, so let's go ahead and check our answers. Yes, yes. Yeah. So I was going to ask you, but. Okay, so now that you have all those y values, so I want you to plot the points. So I'm circling the x value and the corresponding y value. So please go ahead and graph those. So if you just got here or you're not in class and you're watching this video, I want to remind you that you will have 2.6 and 3.1 assigned as homework. The due date for second period will be Wednesday, October 28th, and the due date for seventh period will be Thursday, October 29th, which is my birthday. So you better watch that video and do the homework. So 2.6, I know we didn't finish covering it, but it is important that you do learn that. I don't feel very comfortable skipping that material, even if it makes you happy. So I'm going to start graphing mine. Sometimes it's easy to start with the positive x values. Okay, and so where would you say the y-intercept is located at? Zero for x value, 1 for the y value. Very good. Now, do we have an x-intercept? We do not. And so we could say NA. Now, instead of having an x-intercept, we have something interesting that it's called a horizontal asymptote. And that horizontal asymptote will be this horizontal line with the equation y is equal to 0. And so our y values are going to, if we keep, let's see if you guys remember arrow notation. So as x approaches negative infinity, so that means follow the marker. If I go in this direction, and I keep going, f of x is going to approach 0. It's not going to be 0. It's always going to get smaller and smaller. And what I mean by that are those y values that we see here. So if I was to find f of negative 4, it will be 1 over 16. If I want to find f of negative 5, it will be 1 over 32. And so it just keeps getting smaller and smaller and smaller, but it will never be 0. Okay? It doesn't matter how far you get on the left or how much your x values decrease. It will never be 0. Sometimes when you graph it on a calculator, it might look like it is 0, but it's not. Okay, so now I want you guys to work this table. So that was not me. The reason I said you don't need a calculator is because we can do it by hand. So I like to always start with 0. So we will have 1/2 to the power 0. And so almost anything to the power 0 is equal to 1. So the value for g of 0 should be 1. And yes, we can see that it is true. Now let's go to the positive values now. So now we have 1/2 to the power 1. So that will just be 1 over 2. The next one is 1/2 to the power 2. So when you do that, you need to make sure that you distribute the exponent to the numerator, but also to the denominator. So that will be 1 to the power 2 and 2 to the power 2. So that will become 1 over, what is 2 squared? 4. The next one will be 1/2 to the power 3. So again, we must distribute the exponent to the numerator and the denominator. So that will be 1 cubed over 2 cubed. And so that will become 1 to the power 3rd is 1. 2 to the power 3rd is 8. So that will become 1/8. So let's check our answers. 1/8, 1/4, and 1/2. Now let's go to the negative exponents. Let's see what's going to happen there. So here we have 1/2 to the power negative 1. So if I distribute the exponent like I did down here, it will be 1 to the power negative 1 and 2 to the power negative 1. Yes? Now, I don't want to have negative exponents, so what I'm going to do is just switch them or flip them, or the reciprocal of it, and that will be 2 to the power 1 over 1 to the power 1. So that is just 2. Now, g of negative 2, now the x is going to be negative 2. So that's going to be 1/2 to the power negative 2. And this will turn into 1 to the power negative 2 divided by 2 to the power negative 2. Now, we use that rule where we flip them. And then it will be 2 squared divided by 1 squared. So that will be equal to 4. Just 4. The denominator is still 1, right? Because 1 squared is 1. Now the last one that we have here, 1/2 to the power negative 3. So that will be 1 to the power negative 3, 2 to the power negative 3. And this will become 2 to the power 3, 1 to the power 3. And this will be 8 over 1, or just simply 8. So we have a 2, a 4, and an 8. So now what I want you guys to do is to graph them. Take the x values and the y values, and those are your order pairs. So plot those points, and then connect them with a curve. So to graph it, I like to start always with 0 because that will give you the y-intercept. Then it is good if you start with the negative x values because the y values are integers. So when x is negative 1, the y value is 2. When x is negative 2, the y value is 4. And when x is negative 3, the y value is 8. Now on the right side of the y-axis, when x is 1, y is 1/2. When x is 2, y is 1/4. And of course, you don't need to be so precise here, as long as you do not touch the x-axis. And so remember that the arrows at both ends, they imply that the function extends indefinitely in both directions. So one thing that I forgot to mention from the previous graph, but it also applies to this one, is that the domain is all real numbers. Now, do we have a y-intercept here? Yes, and that is the point 0, 1. Do we have an x-intercept?
No.
No. Instead of that, we have a horizontal asymptote, and that is the horizontal line, y equals 0. Let's see if we could figure out what would be the range for this. Oh. Not Korean. Very nice. Not including 0 to positive infinity. Now let's look at the other graph, the one above. And we could see that they share a lot of characteristics, right? The domain is also all real numbers. And the range is also the same. The smallest y value is 0 without including x, so that's why Kenny told me without including 0, and that's why I use parentheses. And then it extends indefinitely, so the biggest y value, we will use the concept of infinity to denote that. Now, what is the difference between those two?
One's exponential decay and the other is growth.
Okay, very good. So we could say this is growth, exponential growth. Yes. Correct. Not included, parentheses. Included, bracket. So the first one is exponential growth. And what is the base for this exponential equation? 2. So anytime your base is greater than 1, you're going to have exponential growth. Now let's look at the second one, and you guys could see it. Remember, we always read them from left to right. So in this case, this one will be exponential decay. And what is the base for this one? 1/2. So anytime your base is less than 1, but still positive, that's why we say greater than 0, we will say that we will have exponential decay. Now, the graph of this one, it is comparable to the graph of 2 to the power negative x. So let me call that function h. So h of x, 2 to the power negative x. So if I compare that one to the first function that we graphed, actually, let me just write it here. So f of x is 2 to the power x. And then the one that I have down here, h of x is 2 to the power negative x. If you guys remember transformations, what happens when you change the x values from positive to negative, or from negative to positive? Okay, so we have a reflection across the y-axis. All right, so let's go to the next slide. Is that 25 already? Oh my God. Okay. All right.